This problem involves three identical cylinders. Each cylinder has radius A and weight W. At first, two cylinders are placed on a floor and connected by a link of length 3A. Then the third cylinder is put on top. As a result of the wedging action of the top cylinder, there are forces induced in the link. Our task is to determine forces acting on the link. We begin solving this problem by considering a free body diagram for the top cylinder. We begin by placing the weight. Then we recognize that the cylinder is constrained by the bottom cylinders. Because the surfaces are smooth, we place only forces normal to the surfaces to recognize that tangential forces associated with friction or rough surfaces are negligible. Next, we will consider a free body diagram for the bottom left cylinder. Again, we start with the weight. Then we recognize that the top cylinder is a constraint, and we denote that constraint, or better to say, we denote the force corresponding to this constraint by the green arrow. The reason I use green rather than blue is to indicate that this force is related to the force that has already appeared, and the relationship is dictated by the Newton's third law. So these two forces are equal and opposite of each other, or we can say they're parallel and equal in magnitude, but they're pointing in the opposite directions. Next, let us look at the floor. The floor is a constraint. It's a smooth surface, and therefore it constrains only against vertical motion downward, and therefore the force that we put is vertical up. Finally, the link is a constraint, and we suppose that this link operates such that it allows the cylinder to rotate, but it prevents it from translating. As a result, I will replace this constraint with two forces. Next, let us look at the bottom right cylinder. Perhaps it's not surprising that the free body for the right cylinder is very similar to the one for the left cylinder. The weight, the green force, because it is related to the blue force acting on the top cylinder, the floor, and the link. Finally, let me show forces acting on the link. All of them are shown in green because all of them are related through the third law to the forces acting on the bottom cylinders. So, in writing down equilibrium equations, I will not use any considerations involving symmetry. But it is clear that there is symmetry in the problem, and it will be very useful for us to understand what are the implications of symmetry. So let me begin writing equilibrium equations for the top cylinder. I will denote the normal forces by N1 and 1 prime, and I use this notation to indicate that there may be symmetry considerations. And indeed, if I look at the equilibrium equation for the forces along the x-axis, I immediately conclude that the force N1 prime and N1 are equal, and therefore I can denote both of them by N1. Sum of the forces on Y gives me an equation that allows me to find N1, but I'm not going to focus on it right now. I'd rather proceed with writing down the equations and then solving them. Sum of the moments about C is trivial because all three forces intersect the center of the cylinder, or we can say that while the moment equation is satisfied, it does not provide us with any interesting information. Next, let me go to the bottom left cylinder. I show the forces N1 and N2, the reaction of the floor, and I denote the forces exerted by the link by AX and AY. The equilibrium equations are self-explanatory. Please take your time if you need to go and understand them term by term. And again, the moment equation about the center of the cylinder is trivial. The right bottom cylinder, the story is pretty much the same. And now I proceed with the link. For the link, the force equilibrium equations are very simple since they involve only horizontal and vertical forces. And the moment equation tells us that the only force that produces the moment about A is By. Since it's the only force and the moment must be equal to 0, this force must be equal to 0, which of course from the second equation implies that the other vertical force, Ay, is also equal to 0. Finally, the third equation, which is sum of the forces on X, implies that AX and BX are opposite of each other. So let us write this down. And what happens here is that I replace a system of three equations for four unknowns by a system where all the forces are determined, but there is one unknown parameter t. So I reduced three equations and four unknowns to one unknown through elimination. Should not be surprising. It is instructive to show this result in terms of the updated free body diagram for the link. In this diagram, the vertical forces are absent and the horizontal forces are consistent with this condition. So what this free body diagram tells us is that the link is either in tension, as shown, for positive T, or in compression if the force T happens to be negative. Now, what I will do, I will use T as the primary parameter and go back and substitute it into the remaining equations. I will proceed in the reverse manner. So first I will look at the bottom right cylinder. Please pay attention. I replaced the force Bx with T and I eliminated the force By. The equilibrium equations allow me to find the forces N1 and N3 in terms of T. Next, I will look at the equilibrium equations for the bottom right cylinder, I replace the force AX with T. The force AY is equal to 0. And since I have already determined N1 equal to T over sine alpha, I show this force here. Now, if I look at the sum of the forces on X, I conclude that this equation is trivial. So I don't learn anything from the sum of the forces on X equation, which is actually a good thing because symmetry will make certain equations obsolete. Sum of the forces on Y tells me that N2 is equal to T quant alpha plus W. This is obviously a non-trivial equation. Finally, I go back to the top cylinder and show the forces N1 equal to T over sine alpha, write down the sum of the forces on Y equation, from which I conclude that the force T is equal to half of W times tangent alpha. The only thing that is left is to determine tangent alpha, which is easy if I look at the triangle. This is the link. These points are the centers of the cylinder. Bottom left, top cylinder, bottom right. Doesn't take long to find tangent alpha. And the final answer is T equal to approximately 0.57 W. It is instructive to go back and look at the free body diagrams by putting the actual forces so that we can appreciate what the symmetry does. And here's the picture. As you can see, whatever we have on the left is mirrored with whatever we have on the right. Please take a look at these two forces, look at these forces and these forces, these two and these two. I want to point out that symmetry is with respect to the vertical axis. And in this case, the vertical forces appear equal on both sides, while the horizontal forces appear to be opposite of each other, but this makes perfect sense if you think about symmetry. Another point I would like to make is the following. If we have recognized symmetry from the very beginning, we probably could have started with the free body diagrams that are much simpler than the one that we used. So we could have used this force is one unknown. Another unknown is this force and this force. So we have only three unknown forces, and of course this force could be determined by writing down some of the forces on Y, and the remaining two forces could be determined by writing some of the forces on X and some of the forces on Y. In this case, this cylinder does not get involved because it is symmetric to the left cylinder, and symmetry means that if you adopt it, you have to solve less equations, and this is possible because a lot of equations become trivial.